Let me first explain perhaps the title of this talk. It's a general audience, I understand, so I'll try to make at least words in the title to be semi-understandable. So nanolight is the sort of the key word here. I thought it's an appropriate word for imaging series. Imaging with ordinary light, with wavelength limited light, is pervasive in daily life and in technology. But unfortunately, this form of imaging has significant limitations when it comes to seeing small objects. And unfortunately, that's the task we are commonly facing with the physics of new materials. New interesting effects, in particular quantum effects in materials, often occur at length scales much shorter than the wavelength of light. The problem is particularly acute in infrared range, where the wavelength of light could be 10, 100, or maybe even 1,000 microns long, whereas the features that we are trying to resolve in our experiments are usually smaller, could be on the nanometer scale. So we are facing sort of an intrinsic problem of a mismatch between the wavelength associated with our probe and the length scales that we are trying to resolve in our problem, in our materials. And it's as we are encountering a small problem of optical experiments. A small problem is that you can't see anything small, because diffraction stops you from doing this. And that's where nanolight comes to the rescue. Nanolight, or subdiffractional light, is about coupling a light source with a scanning probe instrument. And the scanning probe instrument there are many versions of them. Essentially, it's in simple terms, it's a sharp needle of an atomic force microscope, or of a scanning tunneling microscope. And the whole idea is extremely simple. You collect useful signal just from the area underneath the tip of this apparatus. And even with commercial tips that you can readily buy for very moderate prices, you go into sort of single-digit nanometer length scales with this type of apparatus. The rest of the optical path is in the free space, so you can put any light source you want here, and that's how you collect the signal just from underneath the tip. That's how you get to the nanoscale. That's what nanolight is about. It's not only a buzzword. It's a reality of our experiments that we are doing on a daily basis at Columbia. And then you raster scan your sample or your tip, and you obtain maps of an interesting contrast that tells you hopefully something about the physics you are trying to investigate. This image may seem like a cartoon. It's not a cartoon. It's an image produced by atomically narrow domain walls in a twisted Waals Materials. These domain walls are only a few atoms wide, and nevertheless you can obtain with nanolight, you can visualize these properties, and you can understand the physics of this material. So that's what we are doing at Columbia in a nutshell. It's a pleasure to work with two Simons Fellows who joined us at Columbia. Dori Halbertal is wrapping up his visit before going back to Israel. Zongtian Zhan is continuing in our group. And this is a headline message of this imaging series talk. I will try to tell you a little bit about the new physics that we investigate with new imaging methods that we develop in our group at Columbia, and we apply it to new quantum materials. So let me spend about a minute on how we create images. I have a little gallery for you here. And these images, I think, don't require much explanation. And that's why we like images, perhaps, in the first place. They tell a story. A good image tells a story without a narrator. You don't need words to go along with that image. And but what I'd like to focus is how these images are created. So photons, of course, have been used for imaging since the beginning of time. And when we want to image something smaller, we often resort to electrons. With electrons, we can easily visualize individual atoms if we set up experiments properly. When we use nanolight, our imaging agent is neither photon nor electron, and the photon and the electron at the same time. In spite of their different nature, photons and electrons, light and matter can be united. When light impinges on a material, it's quite common for electrons and photons to hybridize and to form new quasi-particles that we refer to as polaritons. These do not need to be electrons. Any dipole active excitation in a material, and these polaritonic effects are particularly apparent when we use nanolight in this type of experiments, when we work with experiments with needles. These do not need to be electrons. Other dipole active excitations in materials, like phonons, which are oscillations of the lattice, or excitons, which are electron-hole pairs, so also form polaritons under certain circumstances. So these, and it turns out that these polaritons are extremely informative tools in imaging that really allow us to reimagine how we proceed with optical studies of materials. All polaritons are extremely compact, or could be very compact. The relevant wavelength is much smaller than the wavelength of light by many orders of magnitude. And this is wonderful. And this was really our initial motivation, sort of to start with nanolight. We wanted to go to short length scales and to see subdiffractional objects. But in the course of doing this, we discovered that we signed up for something bigger. And with the help of polaritons, we can really reimagine how we proceed with imaging and with optical studies of materials. And the key thing here is that these polaritons are not static. They are very much mobile. They can be launched by these antennas of our nano-optical instruments. And we can visualize in real space how they travel, how they bounce off sample edges, how they become reflected in non-uniformities in our materials. And from this real space data, we now learn new physics. It's sort of a different approach compared to conventional optical spectroscopy. And we are extremely excited with this approach. And I'll try to tell you how it works and what new things it tells us about physics. So let me tell you how it's done. We start with a quantum material of interest. We flood the entire scene with light. Usually we like to use infrared light of very long wavelength because relevant physical phenomena reside somewhere in infrared range. And then we put a scatterer somewhere in the scene, the scatterer that's much smaller than the wavelength of light. Usually it's an apex of this optical antenna, of a tip of the near-field apparatus. And so this local scatter acts as a scatterer. So it launches this polaritonic waves that can travel anywhere away from the apex of the tip. Polaritons can only live inside the crystal. So as soon as they reach the edge, they have to come back. And then this optical antenna outcouples these polaritonic waves, sends light back to the detector. That's how we record our signal with ordinary detectors. And so I'll show you a piece of raw data here. you form here basically a standing wave between the apex of the tip and the edge of the sample. And when you scan this tip from the interior of the sample to the physical edge, you go through minima and maxima of this standing wave pattern. And from the periodicity of these oscillations and from the wavelength of these oscillations, you learn about the electronic phenomena from visualizing these hybridized quasi-particles of light and matter. Often, this idea of launching polaritonic waves with a local scatter is compared to what you get by throwing a rock on a pond. And I think it's a very good analogy, and I like it. And I have a version of a local analogy. So we'll use the El Dorado building as a cantilever holder. And when light impinges on this cantilever, and there is very strong electric field produced at the apex of this antenna, and this antenna start launching polaritonic waves that travel everywhere away from it. You can learn a lot about water by studying waves on water. And what we are doing in our lab at Columbia, we are learning about electron fluids or excitonic fluids in materials by essentially visualizing the same type of waves. So this is the outline of my talk. I hope I gave you some flavor of what imaging is about. It's about this nanolight combined with scanning probes. But I'm yet to tell you about up-at-night physics issues that we are trying to resolve with these methods. And I will tell you a little bit about programmable phenomena in quantum materials, effects that we produce on demand with various means. And I will tell you why imaging is good for that. And a very specific programmable effect is something that Aaron Sternbach in our lab recently recorded. This is actually work is a collaboration with Angel Rubio and with Simons with Flatiron Institute. And this is about producing on-demand, non-intuitive properties. We call that hyperbolic properties in tungsten selenide. I will tell you about atomically narrow domain walls and how they bounce polaritons in materials. So this is the work that Dori Halbertal has contributed to. Dori is in the audience. Thank you for attending this. And if time permits, I will tell you a little bit about machine learning and how it changes everything we do in our lab now. Okay, so programmable quantum materials, that's the term we like to use at Columbia. And I'll give you one slide sort of introduction to this. For me, this slide is about how lucky we are in condensed matter physics. And that's because it's feasible now to create on-demand new quantum effects, new quantum phases, and in different classes of materials, especially these imperfect metals and imperfect semiconductors of van der Waals, of layered crystals, are particularly amenable to this on-demand control. If nature doesn't provide us with a quantum phase we wish to investigate, we go ahead and create it. And I think this is really great because we no longer need to remain passive observers in condensed matter physics. We can actively and predictively modify materials beyond passive observations, and that's how we get access to new physics. Some of these effects are persistent. Other effects are fundamentally non-equilibrium. They only exist for fractions of a second, for picosecond, sometimes for femtosecond, but we have access and we have to these, and we have means to investigate this. And this diagram shows the tuning knobs that allow us, in combination of these tuning knobs allows us to produce on demand these quantum phases. We start with electrostatic gating. We go to a very interesting form of heterostructuring, twisted heterostructuring. We We go to magnetic field, then we go to electric field. These stimuli are assembled in the order of ascending energy. This is about excitations agitating certain modes in these materials and producing sort of targeted excitation of different classes of effect. And the combination of all these stimuli allows us to produce phases with controlled properties, on-demand properties. That's what we like to call programmable quantum materials. Polaritonic imaging is helping us to make advances with this direction, with this line of research. And why is that? Why polaritons are informative? There are many ways to answer this question, and I'll just quote you a viral tweet that I recently read that I think is very good for my talk and maybe for the series. Seeing is knowing, and not seeing is not knowing. This is this font is a little funny, but I hope everyone can read it. And this is more or less describes very in just 44 symbols what we are doing in our lab. So Waals Materials is sort of is one protagonist of what we are doing in our group, and this is about layered crystals with atomic planes held together by van der Waals interaction. And it's easy to peel off these planes and to isolate single atomic planes. And graphene is an example of this isolation, and also a topic of and the subject of the 2010 Nobel Prize in Physics. Van der Waals Materials host a remarkable portfolio of properties in these single atomic layers, starting from metallic behavior in graphene, some of the best insulators, also observed in atomic layers. Now this is boron nitride, for example. Many exotic and interesting superconductors belong to this class of materials. Magnets, antiferromagnets, and ferromagnets are also now available in the form of single atomic layers. There are excellent semiconductors with light-emitting properties also available in this monolayer form. And then one can start from these layers and assemble them in heterostructures. In heterostructures with distributed properties where neighboring proximal layers carry complementary functionalities. These twisted heterostructures are particularly informative. These different classes of electronic and magnetic effects, they also imply very strong, sometimes very strong dipole active modes, and that can hybridize with light and can lead us to a variety of polaritons. So you know, over COVID lockdown, we, together with Ana Arsenio Garcia, who I think is here, we counted some insane number of these polaritons, you know, and we summarized that in the live review. For example, plasma polaritons in metallic layers of graphene. Phonon polaritons here, a Cooper pair, plasma polaritons due to superfluids, magnet polaritons, exciton polaritons. Frank Wilczek proposed a polariton due to dark matter that some people are trying to observe with this type of, possibly with this type of measurements, not necessarily with nano. I think they should start using nanolight. Maybe they'll make faster progress. So this is a very broad concept. That's right. And this is a little gallery of images, of polaritonic images that I prepared. This is how textures due to plasma polaritons propagating in the network of very narrow domain walls look like. These are phonon polaritons in crystals of boron nitride. These are exciton polaritons that we produced on demand in tungsten selenide. So by visualizing these polaritons, because polaritons are half light, half matter, we get access to all these different effects in van der Waals materials in a novel way that's yet not very well explored. At all instances, the wavelength of light is much longer than the features we observe, so all of this work depends on nanolight. So the physics of polaritons is captured in this dispersion relationship that appear in many textbooks. Pretty much every standard solid-state textbook has a version of this dispersion plot. But only recently, with the advent of nano-optics, it became possible to visualize the propagating character of these polaritonic modes. So the dashed line here is a light cone, and somewhere in this shaded area, there could be a material resonance residing. This could be a phonon mode, this could be an excitonic feature, and when light and matter hybridize, this dispersion splits in the two branches. So this dispersion is a graphical statement of mode splitting. And mode splitting is familiar to us from many physics scenarios, starting from mechanical systems, going to circuits, and all of polariton physics is in this splitting, in this partitioning of dispersion in the two branches. At small frequencies and k, these polaritons are not that different from the photon. But then interesting things happen at higher k, where this line bends to the right of the photon cone, and this region of the dispersion is becoming more metal-like. And then there is this very special region in the dispersion connecting these two sort of extreme behaviors, and that's in this region you are fairly far away from the light cone, so you have very strongly confined modes in this case, but they still have enough curvature to propagate, and we harness these modes for propagation. In this mixed regime, essentially you deal with photons dressed in matter, and photons acquire matter-like properties. And matter, again, could be, there are varieties for matter choices. This could be electrons, this could be excitons, this could be lattice. And that makes things a little bit more interesting. Conventional photons in free space, they don't interact. So there are plenty of photons in the room, but they easily propagate without noticing each other. Photons that are mixed with light start noticing each other. It's a pathway towards strongly interacting scenario in a photon system. Then these photons can be controlled by electric field. And in a recent paper with Andrew Millis, we were able to control these photons hybridized with electrons by passing electrical current through the polaritonic medium. So despite this matter character, this light-like matter does preserve a lot of its photonic ID. These modes can propagate like rays following geometrical optics, even though the wavelength of these rays is deeply, deeply subdiffractional. They are amenable to polarization control, and they can show sort of other light properties associated with light, like entanglement, for example, if you use proper light sources to initiate these modes. How do we visualize these modes? We start by turning on our infrared laser. We tune its frequency to match this interesting region of curved dispersion, and then this dispersion essentially governs the appearance of these waveguide modes that are launched by the tips of our instruments. By the way, I'm happy to take questions anytime. No need to wait till the end. The more questions you ask, the better. No matter how many questions you'll ask, I'll end on time, I promise. So please ask me questions. I'm happy to take those. Okay, so yes, the dispersion governs the wavelength of these polaritonic waves. The role of the tip in this experiment is to convert free space zero momentum light into high momentum modes that can only travel on the surface or through the bulk of the crystal. And then you catch these waves with another tip and send the light to the detector. It's a little awkward sometimes to work with two tips, so we often prefer to place a stationary scatterer somewhere in the scene that we illuminate with long wavelength infrared light, and we visualize polaritonic waves that emanate from this scatterer. And from the character of these waves, we learn about the physics of the matter component that's comprising these polaritons. So that's the idea. So I think I'm doing okay with time. I think I covered 90% of my talk. The other half will be about a couple of examples of polaritonic behavior. Yes, please.
Polaritonic solitons, can you observe, excite them, observe them, scatter them off one another?
Maybe you could elaborate what
I meant. Now your polaritons are nonlinear interacting, and very often in those systems, for instance, in the AMO systems, when you have similar polaritons, the nonlinear interaction is such that you can form solitons, which is topologically protected nonlinear waves.
Yeah. Okay.
And yeah.
So that's a very rich topic of creating this type of objects from polaritons. In fact, Andrea Lu, I think, is in the audience, and he has several papers on this topic. So people have observed, not only in theory but in experiments, various versions of polariton solitons, polaritonic skyrmions, and microns, and topological objects carrying some non-trivial charges that you can actually read out from these images, as some group, including our group as well, has been able to demonstrate. And again, you can get to this type of a behavior in with different matter components of your polariton. It could be, so at least I'm aware of at least 3 versions of polaritons that have demonstrated this type of physics: plasmon polaritons, phonon polaritons, and exciton polaritons in BECs. Okay, so now I would like to tell you about these hyperbolic polaritons. Hyperbolic response is a common signature of many layered materials that's commonly underappreciated. Layered van der Waals materials are usually strongly anisotropic, and it's quite common to find a situation when the in-plane and out-of-plane dielectric function of a material are of the opposite sign. And that's a formal definition of hyperbolicity. So Andrea Lu recently published a comprehensive review on hyperbolic response of van der Waals materials, and I think it's a really exciting topic. And his group is one of the leading contributors in this field. And I'll tell you what we are doing in our work. Hyperbolic materials are perhaps the most exotic materials when it comes to non-intuitive optical phenomena. Common crystals, as soon as the dielectric function becomes negative, common crystals bounce light off. So we have, of course, in New York, a local demonstration of this powerful effect. Light doesn't go inside metals. Everything bounces back. That's the end of the story. but not in hyperbolic media. Hyperbolic media support waveguide modes that can propagate through the bulk of the crystal, despite one of the components of the dielectric function is negative. These waveguide modes are really, really exotic. So you use 6-micron wavelength light to initiate these modes, but they can travel in this waveguide character through crystals that are just few tens of nanometers thick. And yet these waveguide modes fully abide by the rules of geometrical optics. So these are very exotic objects. You see a lot of exotic behavior in the isofrequency surface of these modes. If you have opposite signs of the dielectric function, the isofrequency surface is a hyperboloid. That's where the name is coming from. And it implies many exotic things. For one thing, you have access to infinite wave vectors. Anything infinite in materials is a rare occurrence, and certainly in hyperbolic media, that's what you get. So that's because you have so high wave vectors, the spatial resolution of imaging in hyperbolic material becomes limited with interatomic spacing. Optics and interatomic spaces do not often come in the same sentence, and that's what hyperbolic media again delivers. Please question.
It sounds to me as if this is a whole new area for signal processing in chips and materials. So, we've got BAW, we've got SAW, what we're currently doing, but to be able to process chips in micromechanical spaces, it sounds like there's a whole new set of things we could do there.
Can't agree better with you. I think. Thank you. I think we are all, as a community, we are just beginning to explore and to understand what are the wonders that hyperbolic media can deliver, both in science and in applied sort of sense. And so, thank you for this comment. So the story, as far as I know, of hyperbolic media starts with the physics of plasmas in the 70s. And then in maybe 2 decades ago, metamaterials community has explored this in a very important way. Andrea Lu, again, who is here, and also Vinod Menon also in New York at the City College is another key contributor to this line of work. Our group was the first to visualize this waveguide mode in one of these van der Waals insulators, boron nitride. And today I will tell you of new experiments of getting this behavior on demand. So how we can visualize these modes? So that's what we did. We worked with boron nitride. Boron nitride has 2 infrared phonons at very different frequency ranges. And so there are 2 regions in the frequency axis where you have this hyperbolic behavior. And to confirm this hyperbolic behavior, we placed the crystal of boron nitride above a small antenna, sub-diffractional antenna, smaller than the wavelength of light. We illuminated it with infrared beam. And we expect the edges of this antenna to launch this polaritonic wave that in general propagate along conical trajectories inside the crystal, starting this waveguide mode behavior. So one disk is expected to produce 2 hot rings on the top surface. Of course, polaritons only live inside the crystal. So to visualize them, we had to come with a nano-optical probe. We had to outcouple these modes, and the image on the top is raw data, raw nano-imaging data showing 2 rings that I hope you can see through these slides, and that brings us to the work of Aaron Sternbach at Columbia. So there are many materials that potentially could be hyperbolic. But in practice, there is always little something in the material properties that prevents them from doing this. And because we And maybe we found a naturally hyperbolic crystal. This is a collaboration with Andrew Millis and Raquel Coeras, who is also in the audience, I think. So, but that's under review, and I'm not going to talk about this. But this is how we created this electronic state on demand by photoexcitation. So we worked with tungsten selenide. It's a layered semiconductor, maybe not so exotic, at least now. And it's as far as this behavior, it's an ordinary crystal. At low frequencies, both components of the dielectric function are positive. So what Aaron did, he illuminated this crystal with light, photo-excited this crystal with light, and we thought that this was sufficient to produce hyperbolic behavior, and we wanted to verify it through exactly the same experiment with this antenna underneath the crystal. So we photo-excite the crystal, and we synchronize our probe pulses with this pump pulse. Technically, it's a really challenging experiment, and Aaron Sternbach has done incredible job with building the system first and then executing these measurements. And so then we expect, again, the same thing for this antenna to launch, to produce two hot rings on the top surface. And this is what Aaron has obtained. This image is taken at negative, what we call negative time delays. That means the pump pulse hasn't arrived yet to the crystal. So the crystal is at equilibrium. So in this image, perhaps you see just nothing. That's the whole purpose. So it's a uniform contrast. But we do know that there are these two gold disks sitting underneath the crystal. But the crystal is thick enough so that we don't reach with nanolight to this crystal in the absence of waveguiding. Then the pump pulse arrives. It transformed tungsten selenide in a new electronic state supporting hyperbolic waves. And now we do see these two rims surrounding these golden antennas. This effect is short-lived. At least it's lived only for maybe several tens of picoseconds. That's the time over which this exotic electronic state exists. Then it dies off. But this, as far as I know, this is the first demonstration of hyperbolicity. When we started this work, we thought that we are going to produce hyperbolic plasmons. Yes, please.
What the duration of the pulse that you were using is? So you're sure that the time scale is the material response, is not the pulse duration?
Yes. Thank you for this question. So the pump is maybe 150 femtoseconds long. So it's an order of magnitude or more shorter than this pulse.
Thank you.
So it's definitely the relaxation is guaranteed not by the pump but by physical processes in the material. So that's what we have here. So we thought that we will, with this pump, will produce free electrons in the semiconductor. That was our sort of naive thought when we started this experiment. But Simone Latini and Angel Rubio told us that this was not a very good, not a correct idea. And a much more interesting explanation is in terms of physics of excitons. So there are these crystals support very intense transitions. Sometimes they are referred to as Rydberg transitions in parallel to atomic physics. They have incredible oscillator strength, but they're dormant at equilibrium. So in order to get access to this transition, you have to photo-excite your crystal. First, that's the purpose of this pump in this experiment. Once we've populated one state, then we can take advantage of hyperbolicity associated with this inter-exciton transitions. So let me tell you a little bit about Moire. And Moire is about twisting crystals and obtaining extra periodicity. That's what is referred to as Moire pattern. You can see very clearly additional periodicity from two twisted layers that's not present in the individual layer. Moire patterns are commonplace in art, in fabric design, in photography, and now also in quantum materials. And because this effect allows us to produce additional periodicity that modifies essentially all properties of quantum materials, optical, electronic, magnetic, you name it. And this is a very interesting effect because it's a tunable effect. All you need to do is to twist one layer with respect to each other. And this is type of problem that I think just ideal for us, for nano-optics to shine, because these are the length scales that we can access with nano-optical tools. So my colleague Corey Dean took this idea of rotating crystalline layers, single atomic planes, literally. And that's the AFM movie that he has obtained. By attaching some kind of a disk to atomic layer, he can push on it and he can rotate this layer and obtain this movie. So you really get to dialable properties. You can dial any angle you want, and you can get different behaviors from these properties when you want. And this is as close to science fiction as I ever been in my career, and this is amazing that it's not just fiction but science facts now, and that it all works. So nano-optics has allowed us to visualize, with the help of polaritons, has allowed us to visualize these domain walls and to understand the physics of these domain walls. And we were very happy that we would decipher this physics from these images. So let me summarize to be on time, and I'd like to leave some time for questions, hopefully in the end. Polaritonic imaging has allowed us to reimagine how we learn new physics from optical experiments. In conventional spectroscopy, this is all about color, about how much light of a given color is absorbed, transmitted, emitted. And with polaritons, it all suddenly becomes about shapes and forms and the standing waves that we can form. And with these two examples, I had to rush a little bit through this example, but basically this is a pattern produced by domain walls in van der Waals material, and here is hyperbolic state that we created on demand, and polaritonic imaging has allowed it to decipher this relevant physics. So with this, we now routinely go to places we never thought we would be able to get to. We are beginning to reimagine what we can do next, what kind of problems we can study. Thank you for the privilege of your time.